how artificial intelligence can transform passive reading into active learning through retrieval practice and spaced repetition. We begin with a fundamental question. Why does reading feel productive while actual learning requires something entirely different? The transformation from passive input to active retrieval is where AI becomes a powerful accelerator. Let us first examine the cognitive illusion that traps most learners. When you read a textbook, you experience fluency. The material feels familiar, the words flow smoothly. Your brain mistakes this fluency for mastery. But fluency and mastery are fundamentally different cognitive states. Recognition is easy. You see the answer and think, yes, I knew that. Recall is harder. Generate the answer from memory. Application is hardest. Use the knowledge in a new context. Reading trains recognition. Science requires application. Cognitive science gives us a mathematical framework. Retention is a function of retrieval strength and time. Each time you successfully retrieve information, you strengthen the memory trace. Let me pose a quantitative question. How much more effective is active recall compared to passive review? Meta-analyses show active recall produces approximately 2.5 times better long-term retention than passive review. This is not a small effect. This is the difference between forgetting and remembering after 1 month. Now we examine the mathematics of forgetting, discovered by Hermann Ebbinghaus in 1885. The forgetting curve follows exponential decay. Retention R of t equals 100 times e to the negative kt, where k is the forgetting rate constant. Without review, you lose roughly 60% of new information within 1 day. But with spaced repetition, we interrupt the decay curve at optimal intervals. Each review resets retention to near 100% and slows the subsequent decay rate. The spacing effect is one of the most robust findings in cognitive psychology. The optimal review interval scales with the square root of current retention strength. This is why the intervals grow. 1 day, 3 days, 1 week, 2 weeks, 1 month, 3 months, and so on. Let us perform a back-of-envelope calculation to quantify the time savings from spaced repetition. Suppose you need to master material for long-term retention. Cramming might require 20 hours for 1 week retention. Spaced repetition achieves 6-month retention, with only 8 hours total study time, distributed over weeks. The efficiency gain is not linear, it is exponential. Now we arrive at the revolutionary capability. Artificial intelligence can automate the entire spaced repetition pipeline. The AI pipeline has 3 stages. First, ingest raw material, textbooks, papers, lecture notes. Second, AI extracts key concepts, relationships, and testable knowledge. Third, generate quiz items calibrated to your current understanding. The AI creates a question bank with multiple representations of each concept: definitional questions, application problems, comparative analyses, quantitative calculations, and conceptual syntheses. Each targets different levels of Bloom's taxonomy. The AI calibrates item difficulty based on your past performance and concept distance in the knowledge graph. Items are neither too easy, which wastes time, nor too hard, which causes frustration. This is adaptive learning. Let us examine the cognitive mechanisms that make retrieval practice so powerful. During retrieval, your brain searches for the memory trace using multiple cues. This search process strengthens not just the target memory, but all the neural pathways leading to it. You are building a web of interconnected knowledge. The key insight is elaborative encoding. Each retrieval attempt creates new associations. After 5 retrievals from different angles, you have not memorized one path, you have built 5 independent routes to the same destination. Redundancy creates robustness. Now let me pose another question. What is a desirable difficulty principle, and why does it matter? Learning follows an inverted U-curve with difficulty. Too easy and no encoding occurs. Too hard and you give up. The optimal difficulty is where you succeed about 70 to 85% of the time. This zone maximizes the learning rate per unit effort. We can approximate this mathematically. Learning rate is proportional to difficulty times 1 minus difficulty. Maximum occurs at difficulty equals 0.5, but the practical optimum shifts to 0.75 when we account for motivation. Let us examine the specific question. Types A I can generate to target different cognitive processes. I generates 4 primary question types. Factual recall builds foundational knowledge. Conceptual links test understanding of relationships. Problem solving requires application of procedures. Transfer tasks demand knowledge application in novel contexts. Each serves a distinct purpose. For complex concepts, AI creates question sequences that build scaffolding. Start with component parts, then relationships, then synthesis, then application. Each question prepares you for the next, constructing understanding incrementally. Let me give you a concrete example from quantum mechanics to illustrate the scaffolding approach. Question 1. Define wave function. Question 2. Explain superposition using wave function formalism. Question 3. How does measurement collapse superposition? Question 4. Apply decoherence theory to explain classical emergence. Each builds on previous answers. Now we examine how AI optimizes the timing of reviews using sophisticated scheduling algorithms. The SuperMemo algorithm uses the formula interval n+1 equals interval n times easiness factor times quality of recall. Each successful recall increases the interval multiplicatively. This creates exponential spacing growth. Your rating of recall difficulty adjusts the easiness factor. Easy multiplies interval by 2.5, good by 2.0, hard by 1.2. Again, cuts it in half. The algorithm adapts to your actual forgetting curve for each item. The algorithm estimates your probability of recall as e to the negative t over tau, where tau is the memory half-life. It schedules reviews when probability drops to approximately 85%, maximizing efficiency. Beyond spacing, AI implements interleaving, mixing different types of problems rather than blocking them by type. Locked practice. Solve 10 calculus problems, then 10 linear algebra problems, then 10 differential equations. Interleaved practice. Mix all 3 types randomly. Interleaved feels harder, but produces superior long-term retention and transfer. Meta-analyses show interleaving produces 43% better performance on delayed tests compared to blocking. The mechanism is discrimination learning. You learn not just how to solve each type, but how to identify which type you are facing. AI provides real-time feedback on your metacognitive accuracy, how well you know what you know. Before answering each question, you rate your confidence. The AI tracks calibration, the correlation between your confidence and actual performance. Poor calibration means you have illusions about your knowledge. Perfect calibration lies on the diagonal. When you say 80% confident, you are correct 80% of the time. Overconfidence lies below the diagonal. The AI surfaces these discrepancies, training you to accurately assess your knowledge state. Let us calculate the efficiency gains from treating learning like a memory gymnasium. Traditional approach. 100 hours reading yields 20% retention at 6 months. AI approach. 40 hours total time, 30 hours reading plus 10 hours spaced retrieval practice yields 85% retention. You spend less than half the time and remember more than 4 times as much. The efficiency ratio is knowledge retained divided by time invested. For the AI approach versus traditional, this equals 0.85K over 40 hours, divided by 0.2K over 100 hours. Simplifying, we get 10.6 times greater efficiency. This is not a marginal improvement. This is an order of magnitude enhancement in learning productivity. What happens in the brain during retrieval practice? Let us examine the neuroscience. Each memory is not stored in a single location, but distributed across a network of neurons. Retrieval activates this entire network. The activation strengthens synaptic connections through long-term potentiation. Hebbian plasticity. The change in synaptic weight equals learning rate times presynaptic activity times postsynaptic activity. Neurons that fire together, wire together. Each retrieval strengthens the wiring diagram. Neuroimaging studies show repeated retrieval produces structural changes, increased dendritic spine density, enhanced myelination of axons, and larger synaptic boutons. These physical changes encode long-term memories. Testing is not just assessment, it is the learning intervention. This is called the testing effect. Each test creates a new memory trace, distinct from the original encoding. This is why testing yourself creates better retention than studying the same material again. You are not reviewing one memory, you are creating parallel redundant memories. The testing effect is robust and general. It is not just about testing. It is about the act of retrieval itself, which strengthens memories and promotes long-term retention.